Right. Morning, everyone. Just going to give everyone about another minute to join, and then we'll go ahead and get started. All right. It's 9 o'clock, so I'm just going to go ahead and jump right into it. So thank you guys so much for joining us this morning. We're really excited to have you guys, and we're going to talk about some toxic metals in pharmaceutical products. So I'm just going to go through a few housekeeping items before we jump into it. So if you have any questions throughout the presentation, you can post those in the Q&A feature. So there's a chat feature and a Q&A feature. But if you could, please just submit those to the Q&A feature. That'll help us keep track of those a little bit better so we don't miss any. The presentation will be recorded, so you'll get a copy of it after we conclude today's session, and you'll also get a copy of the slides as well. So I'm just going to go ahead and jump into it. So in the first section, I'm just going to go through kind of an overview of the USP 232, 233 method, and ICH Q3D. So USP is United States Pharmacopoeia. ICH is the International Conference on Harmonization. So Chapter 232 specifies the limits for the amounts of elemental impurities in drug products, and then 233 describes the procedures for actually testing those. So as of 2017, USP 232 and ICH Q3D have been fully aligned with respect to elements, concentrations, and toxicity classification. So why do we want to test for these toxic elements in drug products? Well, it's because of the adverse health effects that can come about from being exposed to high levels of these. So those effects can be from mild to severe, depending on the person who's exposed, their life stage, their age, and their health prior to being exposed, as well as the route of exposure. So all of those things are going to play into what kind of effects are going to be seen, but they can be very severe, as I said, if you have small children and babies, because these are going to be neurological effects from some of these heavy elements. It's also going to matter what form of the element that you're exposed to, because the form is going to determine how that compound or that element is able to react and interact within the body. So these are just some examples of some recent current events where these concerns for heavy elements or heavy metals have been brought to light. So I'm not really going to go into these individually, but I've posted some links here that you can look at if you're interested in learning more about those. But it's really just to show that these concerns and these testing methods are very relevant and prevalent in our society. So it's important that we're able to accurately test and quantify these levels of toxic elements in a wide range of product types. So these are the elements that are included within this method. So they're color-coded by class. So I'm going to go into this a little bit more detail in the next slide. This is just to kind of show you that it does take up quite a large portion of the periodic table because there are 24 elements included in both of these methods. So class 1 are what we call the big four. So these are arsenic, cadmium, lead, and mercury. These have a really high level of toxicity, and they're not really used in the manufacturing of drug products, so they shouldn't really be present in those products. So it's really important that we are able to test very low levels of these because the limits are going to be really low, because these are going to have those really highly toxic effects for people who have a compromised health. So then class 2 is split into 2 different sections. So there's the class 2A and class 2B. Class 2A are going to be more likely to be present in pharmaceutical products because they're often going to be introduced during the manufacturing of these products. So those are in there because they're likely to be present. Class 2B are less likely to be present, but they do still have a high level of toxicity. So we want to make sure that we're quantifying any of those that are present in drug products. And then class 3 are those that are really going to be the toxicology or toxicological effects are going to be heavily dependent on the route of exposure. So if it's an oral medication, they're not really going to be too much of a concern. It's going to be a lower toxicity. But if they're being introduced by inhalation or injection, that's where you're going to see some issues with or some health concerns for those. For example, so chromium, if you have chromium in a product that you're ingesting or you're swallowing, all of your chromium is going to be converted to chromium-3, which is a lot less in the +3 oxidation state, which is a lot less toxic than the +6. But it's going to be a lot more of a concern if you're inhaling a product that has chromium, because if you have any of that Chrome-6, that's going to be directly introduced into the capillaries in your lungs, and it's going to have those adverse health effects. All right, so in the next sections, we're kind of going to go through just by elements and what issues that you'll have with an ICP analysis of these. So in this first section, I'm just going to go through the big 4, so arsenic, cadmium, lead, and mercury. And then once I finish with these, I'm going to switch it over to our technical support chemist, Ashley Jones, and she's going to do the second half where we go through some of the other elements, as well as some solutions and some standards that you can use for testing these products. So start off with arsenic. Arsenic is definitely one of the big problem elements. So the 3 major issues for arsenic are oxidation state, low intensities on the instrument, and interferences. So for oxidation state, when you think about an ICP analysis, you generally don't worry much about the oxidation state because what you're analyzing is the total content of that element. So you're just looking for total arsenic, and that's still true. But where oxidation state comes into play is that the form is going to affect the volatility. So the arsenic 3 form has a higher volatility than arsenic 5. So you're going to get a much higher transport efficiency to the plasma, which will result in higher intensities from the arsenic 3 versus the arsenic 5. So what we generally see in both ICP OES and ICP mass spec is that there's about a 4 to 6% high bias on arsenic 3 versus arsenic 5. So I'll talk about that and show you some examples in later slides. But the other issues, so low intensity, arsenic, just in general, you don't have many lines to choose from, and it's pretty low sensitivity on all the lines. The 189 wavelength is going to be the best line as far as sensitivity and being free of interferences. But because that's in the lower UV range, a lot of times if you have in a shell system, you're going to have a hard time reaching those low detection limits just because you don't have the intensities. An Orca optic system is going to work better. You'll get higher intensities, but you'll still have some interference effects in that range. So if you're analyzing on mass spec and you have any chloride present, arsenic is monoisotopic, so it's at mass 75. So if you have any chloride present, there's a significant argon chloride interference that shows up on that mass 75. So you're going to want to use KED mode or collision cell, which is helium mode, to break up that polyatomic interference. So you could also have a calcium chloride interference because calcium is also mass 40, so 40 and chloride, which is 35, is also going to show up there. So definitely want to make sure that you're using collision cell if you have any chloride present at all. So for OES, the 228 wavelength, which is relatively sensitive for arsenic, you generally can't use if you have any cadmium, which is in this method, because there's a major cadmium interference. And since cadmium's a higher sensitivity, it's going to really affect your arsenic and potentially cause you to get a high bias on arsenic or a false positive. Lastly, so if you have any carbon, which you always have some carbon, but if you have high levels of carbon in like an organic sample or something where you've done a fusion with a carbonate, you're going to get significant interferences and signal enhancement in the lower UV range, which is below 190. So this is going to cause issues for any of those wavelengths that you're looking at in that lower range. So this is an example of what that high bias is going to look like for arsenic 3 versus arsenic 5. So the green line is a certified 10 ppm standard for arsenic 3, and the purple line in the same way is a certified standard that contains 10 ppm of arsenic 5. So you can see that there's a significant difference in that intensity that you're getting from that peak. So the main thing that you need to look for is that you want to make sure that all of your arsenic is in the same form in your standards and your samples. So if you boil with nitric acid or you have a strong oxidizing agent, you can make sure to transition everything to arsenic 5. But if you have any arsenic 3, it's going to affect the sensitivities and maybe give you a false high result. So you want to make sure that you have arsenic in all the same form. So all of our standards are going to be in only a single form. So our CGAS standards and the MSAS standards, those are all going to be arsenic 5. Those are from the arsenic metal, which we convert to arsenic 5 through reaction with nitric acid and hydrogen peroxide. And then any of our speciated standards, so CGAS parentheses 3 or CGAS parentheses 5, those will be arsenic 3 and arsenic 5 from the oxides. So one other thing that you want to make sure to account for is your peroxide. So if you're using peroxide in the digestion, you want to make sure that it's all gone before you try to run your samples, because so we generally think of hydrogen peroxide as an oxidizing agent, and it is when it's concentrated and when you're heating. But once you get to room temperature and have a dilute hydrogen peroxide, it can also act as a reducing agent. So if you have residual hydrogen peroxide, you can actually convert some of your arsenic 5 back to the 3. So you just want to make sure to heat that until all of the peroxide is gone from your sample. So how can you check to make sure that you have all one oxidation state and you don't have any of the other species present? So one thing you can do is you can use a chromatographic method. So this will separate the species to where you can see if there's a peak for both. We use ion chromatography to check for the presence of one in the other. But you could also, if you have a HPLC, ICP, or something that's a chromatographic method coupled with your ICP, that's also a really good option to ensure that you're not getting both. And even if you are, you can quantify them separately. So one thing to keep in mind, if you haven't used a chromatographic method for arsenic before, is that you may think that you would need a cation column because you're looking for +3 and +5, but arsenic actually has no cationic chemistry. So even though it's in the +5 and +3 oxidation state, it will always be in there as a compound, which is an anion. So arsenic 5 will be arsenate, arsenic 3 will be arsenite. So another way that you could check for arsenic 3 in your arsenic 5 standard is you could perform an iodometric titration, which is another method that we use in-house to ensure that the arsenic 3 is not present in our standards. So if you have any questions about this, feel free to reach out and we can provide some guidance on the best way that you might be able to confirm the oxidation state. This is an example of a chromatogram for two different standards, one containing arsenic 3, one containing arsenic 5. And so we were checking for the presence of one versus the other. So we ran standards of both. So you'll see that giant peak in the middle that looks really gross. And what that is we, our standard for arsenic 5 is an acid matrix. So to run that on an anion column, you would have to neutralize that. So we had to neutralize the nitric acid with sodium carbonate. So that giant peak in the middle contains carbonate and also nitrate. So just be aware of that if you are using this method, that you may have an interference or other peaks show up from the anion of your matrix components. All right, so the next of the big four is cadmium, but luckily cadmium is by far the easiest of the big four to analyze. So I'm not going to spend too much time on it, but it has many good sensitive wavelengths and multiple masses to choose from, whether you're running on OES or mass spec. So I've just listed the interferences here, same as I mentioned for arsenic. 228 wavelength will have that arsenic interference, but like I said, there's lots of other good wavelengths that you can use as an alternative, or you can just ensure that you have decent separation of the arsenic and the cadmium, because cadmium is going to have the higher intensity. But the best option is usually just to choose a different wavelength that's free of those interferences. On mass spec, multiple masses are going to have tin and molybdenum interferences. So you'll just want to watch out for that and either use a mass that doesn't have those interferences or account for those interferences, and I'll show you how. So this is our isotopic abundance table. This is a really good resource for any ICP mass spec analysis. So it's going to really help you in the method development phase to choose masses that don't have interferences, or just be aware of the interferences that you're going to have to account for. Or if you've already run the analysis, it's helpful for identifying any issues that you're seeing and help identify what interference is causing those issues. So all of the isotopes that are circled in red are isobaric interferences, and the ones in blue are polyatomics, and they're all oxides. So the way this is set up is that each box is 16, each little table there is 16 mass units apart from the one right above it. So the isotopes in the column right above the analyte that you're looking at are going to be the oxide interferences. So if you have any of those elements present, you know that you need to make sure that you're looking for the oxide interference and use a different mass again, or use the collision cell to break up the polyatomic. So for polyatomics, we can help with those by breaking up using KED mode, but what about isobarics? So these are the ones where your element of interest or your analyte has another isotope of another element that's in your method on the same mass. So you can actually perform correction equations to correct for this. So this is an example of what that would look like. So if you're looking for cadmium 116, but you also have tin, you're going to have tin 116 isotope as an isobaric. So what you would do is you would look for an interference-free isotope of your interfering element, so the tin. So we would look at tin 117. So we would look at the counts on the interference-free tin and multiply that intensity by the isotopic abundance ratio of the line that we're interested in, the 116, relative to the 117. So once you've calculated that, you know the counts on 116 from 10, and you can subtract that from your signal at 116, which will give you the counts that are coming from cadmium, as long as there's no other interferences that are contributing to that intensity. So this is pretty easy to do for isobarics because it relies only on your signal intensities and the isotopic abundances. So you do want to make sure that you know the isotopic abundance. The ones given in the table are the natural abundances. All right, so that brings us to mercury, which is, along with arsenic, one of the most problematic elements for several different reasons. So for mercury, the issues deal with stability, volatility, and adsorption. So I'm going to go through each one of those. I gave them each a different slide because there's so much to consider, and this is such an issue for so many people that I really want to dive into the issues separately. So for stability, for an ICP analysis, mercury has to be in the +2 ion form to get accurate measurements. So these equations kind of give an overview of the issues that we deal with in our standards at Inorganic Ventures from the way that we make them. So what we do is we take mercury metal and we digest a nitric acid, which converts the mercury to the mercury +2, which is what we want. But from the reaction, you also get the off-gassing of nitrogen dioxide, which is those brown fumes that you see upon digestion. And so what we do is we heat it until all of those brown fumes are expelled and we're not getting any more NOx fumes forming. So what we want to have in the end is our mercury ions and the excess nitric, and then we dilute that up in water to make our concentrates and our products. The issue is, if there is any NOx fumes present, this can actually reduce that mercury back to a dimer. So it's still mercury 2+, but it's mercury 2+. So it's a dimer with a +2 charge. And so the issue with this is that when this sees a ligand like HCl, that will cause the disproportionation of that dimer into partially what you want, which is the mercury +2, but will also form metallic mercury, which is volatile. So you could have loss of this species over time because it's volatile and you're losing it from the bottle or container being open to the air. Or if you run the standard while you still have the volatile mercury present, you'll get really high intensities and you'll get incorrect results for your mercury. So that brings us to volatility. So any type of reducing environments can cause formation of metallic mercury as well. So even if you don't have the dimer present, if you introduce the mercury to a reducing environment like triethanolamine or tartrate, you'll form that metallic mercury, which will cause those same issues. So because of this volatility, if you have metallic mercury in your sample, during your sample preparation, if you don't have a closed vessel and a good method for preventing loss of volatiles, you can lose some of your mercury, and so you could get false low results or a false negative. And then again, you'll get really high transport efficiency of the metallic mercury during your analysis, which will give you increased signals of several 100%, or could give you those increases in intensities. So if you're getting really, really high recoveries on mercury, you probably have some metallic species somewhere in your analysis, probably in your samples. And the last thing is adsorption. So mercury in a nitric-only matrix is not stabilized, and it will therefore adsorb to any plastic components that are introduced. So that would be your bottles, your intro system, the tubing, pipettes, weigh boats. So if you do have mercury and nitric alone, you want to either store that in glass because it won't adsorb to glass, or stabilize with an alternative ligand. A lot of people will use 1 ppm gold for stability because it forms an amalgam and will keep that mercury stable. But be aware, if you are using 1 ppm gold, Even if it says it's in a nitric matrix, it will have some chloride because you'll have it's gold trichloride. And so that will cause issues on ICP mass spec, those chloride interferences. So make sure that you're either using KED mode for that, or you're matrix matching. Since it is such a low level of chloride, you can matrix match and spike in the 1 ppm gold from the same source into your standards, blanks, and sample, and that will equalize the effect from the chloride. So what we recommend for mercury generally is using a hydrochloric acid matrix because this is going to prevent any adsorption to plastics. But again, we do realize that if you're running on mass spec, you don't want to have those chloride interferences. So there are some other options, but we've had tons of experience with this. So if you're having any issues, again, please reach out to us. For your intro system, glass intro system is definitely preferred because the mercury is not going to stick nearly as bad, and you won't have those memory effects of carryover into your next sample. But if you do have HF, you can't use a glass system because you'll be leaching all the boron and silicon into your instrument. So you want to make sure that regardless of what intro system you're using, that you have a really robust rinse scheme for mercury to ensure that you're not getting carryover into your next sample that could give you false high or false positive results. So we have a rinse solution called ICP True Rinse. It's a combination of hydrochloric acid and thiourea, and it's really good at rinsing all the mercury out of your system quickly. You could also use 1% ammonium hydroxide. It works really well. A lot of people don't think about a base as being a good rinse, but that's worked pretty well for us in the past as well. If you're not able to use chloride, or if you're analyzing for sulfur, you don't want to use the thiourea. So as far as interferences, the 184 nanometer wavelength on ICP OES is generally really good for mercury. It's got good sensitivity, but again, if you have organic species or if you have just high carbon from any source, you are going to get those carbon interferences because that's in the lower UV range. 194 is a good wavelength as well, but it has a vanadium interference. For ICP mass spec, got a lot of good masses to choose from. However, all of them except 201 will have a tungsten interference. So if you also have tungsten present, you want to make sure that you're using the 201 mass. And that one does have a rhenium interference. So if you have tungsten and rhenium, you may need to use one of those correction equations to get a good value for mercury on mass spec. So that brings us to the last of the big four, which is lead. So lead is less problematic than the others. Not as great as cadmium, but definitely not as big of an issue as arsenic and mercury. The main issue that you'll run into with lead is contamination. Lead is a major contaminant in certain acids like nitric acid, which is a common acid used. So you want to make sure that your blanks are using the same source of nitric acid as well as the same concentration of nitric acid as what's in your sample, so that you're accurately accounting for any level of contamination that's from the acid and not from your actual sample. Same thing with your pipette tips and some other materials that you use in sample prep can have lead contamination. So you want to make method blanks. So what you do is you treat the method blanks exactly the same as you would your sample. So you're putting it into the same vial using the same reagents, putting it through the same process, whether that's microwave digestion or the same sample prep procedures, using the same pipette tips. And that's going to show you whether the lead that you're seeing is actually from the sample itself, or it's from your processing, your reagents, something in your method is adding that contamination. So you would just run those method blanks as samples to see what's being introduced during the process. So another issue with lead is solubility. So it has kind of weird issues with solubility that are kind of different from what we see with a lot of other elements. So most of these are going to be only issues for high concentrations of lead. So if you're looking at low concentrations, which is typical of this method, but if you're looking at like 500 ppm or higher of lead, you can start to have precipitation if your acid concentration is incorrect. So if you're in a hydrochloric acid matrix, you could have lead precipitate as the chloride, but increasing your HCl is going to drive that back into solution. On the other hand, if you have nitric acid and your nitric acid matrix is too high, your lead can precipitate as the nitrate. And again, just diluting with water is going to allow that lead to go back in. But just something to be aware of if you see a precipitate form and you need to figure out what that is. Another issue with lead is compatibility with other elements in your system. So it's really going to be, again, at high concentrations that these are an issue, but the three elements, lead, arsenic, and bismuth, if they're all present at high levels, they can start to precipitate if your acid content is not high enough. So high levels of lead, arsenic, and bismuth, or any combination of two of these, are going to need consideration for high nitric matrices. So if you have any issues with that, again, we can help you out with what concentration will be appropriate. Of course, lead will precipitate as the insoluble sulfate if you have any sulfate present. So you won't want to use a sulfuric acid digestion or sulfuric acid in processing because you'll lose your lead. And then same with chromium. So if you have a chrome 6 species present and you add this to your lead, the lead and the chromium will precipitate as the lead chromate. So just some tips and tricks for things to avoid during your sample prep. And so most of the issues with lead are not with the actual analysis, they deal with the sample preparation. So once you have your samples, you want to run them on the instruments. For OES, we generally recommend the 220 wavelength as being really good for OES with regards to sensitivity and interferences, but it does have a bismuth and niobium interference. So if you have either one of those present, you want to choose a different wavelength. 168 is also good, but again, it's in that lower range where you can have carbon interferences, and it also has a cobalt interference, and cobalt's in this method as well, so I wanted to mention that. On mass spec, the 204 mass will have a mercury interference, so be aware of that. And then 206, 208 have platinum and osmium, which are also in this method, and 207 has iridium, which is also in this method. So you just want to make sure that you're aware of those interferences, and we generally recommend checking all of the masses if you're doing a mass spec analysis for lead. So that concludes the big four. So I'm going to go ahead and turn it over to Ashley Jones to go through some other problem elements and some tips and tricks for prepping your standards.
Hi guys, thank you again for joining us this morning. I just want to pop in here and say before I begin, it looks like we are getting some questions in the Q&A, so please submit those anytime there's anything you would like more information on. If we're not able to get through all of those, we'll answer them offline and send those out. So please feel free. So we go on to our next slide here. Autumn's controlling slides for me, so bear with me. So the first one, this is one that we talk about quite a bit in all of our presentations. I know you guys have heard us speak about silver a lot if you've listened to any of our talks and stuff before. So this is included in those class 2B elements there. So this might not be something that you necessarily have to analyze if you're doing certain classes. You're not necessarily concerned about, a lot of our customers are only worried about the big four, for example. So silver can be a little bit difficult when it comes to interactions with a lot of the elements and the recommended matrices for this method. So our compatibility, it's, as far as other elements go, silver is pretty easy to work with. It doesn't have a lot of inter-element compatibility issues. It's happy with nitric and hydrofluoric acid, which is great because we do have some HF elements here. But it does form more insoluble salts than any other method. It does have that potential. So we want to keep an eye on it. As Autumn was mentioning, our arsenic forms earlier, both forms are typically problematic with silver. So the addition of nitric acid can definitely help with that. But for this method, we want to go to the next slide. For this method, hydrochloric acid, go back one more. For this method, hydrochloric acid is definitely going to be our recommended matrix because of the interactions and the stability and compatibility issues with some of the other elements here. So we definitely want to take silver and silver's concentration in particular into account. So silver will require an excess of hydrochloric acid to maintain solubility. If you have too little chloride, it will precipitate. So luckily, through our years of experience, we have found a pretty easy rule of thumb that we follow when we're designing solutions and when we're recommending them, if you need to have silver in a hydrochloric matrix. So it's kind of a one-to-one situation. So if you have 10 parts per million silver, 10% volume to volume hydrochloric acid would be sufficient to maintain solubility. For higher concentrations, that can be a little bit more problematic because 10% is already going to be, potentially a little bit difficult for your instrument over time. But if you have, say, 20, 25, 30, 40 ppm silver, which is not a crazy high level, but you are going to need a significant amount of hydrochloric acid if you're going to go that route. No matter how much hydrochloric acid you have in the solution, even though we're going to keep it soluble, it is going to be photosensitive. So we'll want to keep that stored out of the light. A question that we get quite a bit in the tech support forums and stuff is that folks are storing their standards in the cabinet and they only take it out when they need to use it, but they're still seeing precipitate. We really recommend to keep silver, if you keep your TCT bag that your product comes in and you fold it over and tape it, that is a great way to keep light out. If you have some other source, a box, a bag, something of that nature, to keep the light out, because even the amount of light that it can be exposed to if you're continuously opening that cabinet for other reagents can be problematic. So this is part of the reason that we offer, you'll see in a future slide, silver separately, because if you combine it in that hydrochloric matrix, you're going to get into a really difficult situation with your acid levels pretty quickly. So go to the next slide, please. Another one that we're going to need to take note of a little bit is antimony. So as Autumn mentioned before, using hydrofluoric acid with a glass system, which is very common, that's what a lot of people are using, it's going to be difficult for your instrument. It's going to start to deteriorate your intrasystem. It will increase silicon and boron concentration as your sample is moving through the intrasystem, because it's going to etch the glass and kind of pull out. It's borosilicate glass, so it's going to pull out those components, and that can really disrupt your analysis. So antimony, again, stable and concentrated hydrochloric acid, but we're going to be using dilute. So there are times that I have seen, if we have lower levels of hydrochloric acid, the antimony is not going to want to stay in solution. One of our alternatives for HF stabilization is to use tartaric acid rather than HF to keep antimony in solution without having to worry about those instrument considerations. If you're using tartaric acid, this isn't going to solve all of your problems. Like I mentioned, I have seen some issues. Tartaric can be a little bit, sorry. Tartaric acid can be a little bit finicky sometimes. It can be picky. And that's one of those elements that, sometimes it works and sometimes it doesn't. We don't necessarily have an answer because it should work on paper. So looking at the benefits of using the tartrate versus HF, if you're using tartaric acid and you're using a nitric matrix, you want to make sure that you're not getting more than 2% volume to volume nitric acid, because an excess of nitric acid will cause the tartrate to precipitate. A thing that I think folks don't think about or don't take into account if you're creating your own standards or you're combining standards in-house is that you need to be aware of the carryover acid. That's something that we take into account when we're designing solutions here and we want to use a tartrate. You need to be aware of what is in the reagents or the standards that you're using that you might be bringing over when you combine those things. So you might have a 2% matrix created, and then you combine other standards or other analytes, and that brings over just enough nitric acid to start to destabilize. So make sure you take that into account. And then also, mercury is included in this method. Tartaric acid is not compatible with mercury. So by and large, the HF stabilization tends to be a little bit more robust, a little bit more reliable, but that's the case with all of our HF alternatives. There are lots of different avenues and options that we have for stabilizing if HF is just a full stop. I mean, there are safety implications. A lot of folks don't want to use it. They don't want to have to change their intro system. And we definitely understand that. So we have some alternatives, but in general, HF stabilization tends to be a little bit more reliable. So that's definitely something to keep in mind. And it may be worth looking into switching out your intro system if these are the kinds of elements that you're going to be looking for pretty frequently. So if we go to the next slide, another one that I think kind of sneaks up on us, it gets us here at IV quite a bit, is thallium. So thallium is pretty benign. It gets along with most of our elements pretty easily, but this is going to be one where we have to really make sure that we're using the correct form depending on the matrix that we want to use. So thallium nitrate, thallium metal are plenty happy in nitric acid, and this will give you the thallium +1 form. And then thallium oxide is going to be soluble in water and acids, and this will give you primarily that +3 form. So if you're wanting to use a hydrochloric matrix, which will be the trend with these types of analyses, you're going to want to make sure that you're using the +3 form, because any chloride presence with the +1 form will cause it to precipitate. So in our stock standards, which you'll see in a future slide, again, those are all made with thallium oxide. They're in that +3 form. So that's one of those things that we can kind of take the guesswork out for you. And it's one of the great parts of having the availability of stocks like this, or even in custom solutions. We can do all of this homework on the front end and make sure that all your forms are going to be compatible, and that your matrix is not going to ruin your analysis before it begins. We'll go to the next slide. So again, our stock product offerings. I'll show you, next slide, please. If you scan the QR code on this page, this will take you to our page on the website where you can see these products. These products, again, are our stocks, which that just means that we create these in a large batch and we bottle them out and we sell them very frequently. If you're not seeing what you need here, or the concentrations that we're offering in these stock products are not quite what you're looking for, we definitely have custom solutions already available. And if it doesn't already exist in our database, we can work with you to design something that will work best for your method. These products on the stock pages are going to be at 10, 100, or 1000x dilutions of those PDE limits. Because as we get into higher concentrations, we're going to have more elemental interactions and things of that nature. So they're a little bit more reliable and easy to work with when we lower those concentrations. But we do have existing custom solutions at PDE limits. They're just a little bit more finagly. We have to be a little bit more careful with our compatibility considerations there. So like I said, if you don't see what you're needing, please reach out to us and we'll work with you on either designing a solution that contains everything, or a couple custom solutions split per compatibility guidelines. But you'll see here that we have some supplemental standards as well as the classes split out. As I mentioned before, in IV Stock 68, we've got silver offered separately. You know, a lot of our folks only need the big four, so we've got those things offered on their own as well. But IV Stock 78 is going to include everything that you'll need. But again, it's not going to be at those PDE limits. So if you're wanting something at a super high concentration, let us know, and we'll work with you on trying to make those elements all get along together. We can go to our next slide. So to talk about creating working standards, whether you're using our standards or you're just wanting to create them in-house from standards that you have already or that you're purchasing from another vendor, it's relatively straightforward with some caveats. So if we can go to the next slide. For ICP mass spec analysis, those lower concentrations are going to be pretty unproblematic. We found that below 1 ppm, most of these elemental compatibility problems that we talk about so often kind of resolve themselves. Interactions tend to be a positive correlation with concentration. So the higher we go, the more problems we'll see. So when you're creating standards at mass spec analysis levels, the matrix is going to be more of the concern. Is going to be the thing that you need to take into account. So again, if we have silver and you're using hydrochloric, it's going to need light protection, or you might want to keep it separately. With mercury at low concentrations, we really recommend hydrochloric acid because there are lots of moving pieces with nitric. With mercury, it will stick to the bottle. It'll need to go in glass at really low concentrations. It's difficult in nitric acid. So if you can use hydrochloric, that kind of solves mercury's problems. And I highly recommend it. And that's what we design most of our solutions in, partly because of mercury. With osmium, again, hydrochloric acid is going to be your matrix of choice. Osmium and nitric acid can form the deadly osmium tetroxide, which could blind you. So if you are using osmium, if this is part of your analysis and you're using nitric acid, we really recommend to make sure that you're keeping osmium as separate as possible. Separate your waste container, because we don't want osmium and nitric to accumulate in that waste container and become dangerous. So again, hydrochloric for its difficulties with some of our other elements, it's really the safest bet here. And then thallium, again, if you're using nitric versus hydrochloric, you'll want to make sure you're aware of your form. And then moly and antimony are HF elements. Beware if you're not using our standard, or even if you are, make sure you know whether you've got something as a tartrate, you have something in a basic matrix. Moly can be stabilized without HF as long as there's no other HF elements present. So just be aware of the other things that you have in solution. And if you're not sure, please reach out to us, and we'll definitely be more than happy to help you with designing your working standards. For our recommended internal standard elements, are pretty simple stock answer are bismuth, germanium, rhenium, indium, lithium 6. Lithium is included in this method, but lithium 6 will still be useful alternative there. This is going to give you a good coverage of your masses, and will be compatible with everything that you have in your method. And again, our matrix recommendation is going to be hydrochloric acid for both of these. When you're prepping for OES, your concentrations are going to be a little bit higher. So if you're in the 25 ppm range, most elements, again, they're going to get along pretty well. Typically, we start to see most of our really difficult compatibility issues at 100 ppm or so. But if you've got silver and you're wanting to use hydrochloric acid and things like that, that can start to be an issue. With our HF elements too, if you have some of the HF thieves included in your method, like aluminum, selenium, these can pull the fluoride away from those elements that need it for stabilization, and can cause destabilization of those HF elements. And again, it could be difficult for your instrument. If you're prepping high, or if you're working with standards that are higher, closer to those PDE limits, and you're prepping, like I said, above the 100 ppm range, that's where we're really going to see some compatibility issues, and designing those solutions closer to the PDE range there are a lot of moving parts. It's a little bit difficult. So chromium at high concentrations will be sensitive to HF, so above 500 ppm. If you have more than 1% HF, chromium will behave like our HF sensitive elements and will precipitate out. Again, molybdenum, antimony, and tin are HF elements, so they may need HF depending on the stabilization option that you're using. But if you don't have HF present, these elements will be happy in a hydrochloric environment. Tin does not need HF for stabilization as long as there's no other HF present and it's in HCl. And then again, selenium and arsenic, those are some of our HF thieves. So if you are using fluoride stabilization, be sure that you're accounting for those when you're adding your fluoride. If you're having trouble with that, you're not sure how much to add, again, please reach out to us and we'll help you with that. Our typical internal standard elements for OES will be happy here. Scandium and yttrium are rare earth elements, which are sensitive to hydrofluoric acid, but they're a little bit more robust, and they can handle a little bit more than most of our rare earths. So they should be plenty happy here. And these are internal standards that most people will already have in their labs if you use those. So we can go to our next slide. So we have a lot of resources, as I'm sure many of you know, in our education tab, but we've also included some specific to this method and to our talk today here on this slide, and you'll have access to these. But we have both 232 and 233 methods, the ICH Q3D guideline. That again is a link to our USP standards on our website. We have some papers from our friends at CEM and Agilent about performing these methods. And we also have a really great new resource on IV Ignite. There's a guide for working with the J value. It's super useful. It makes it very easy to understand what it is and why we need to use it and how to calculate it. We also have a J value calculator that will make your analysis a little bit easier. Those are available in our downloaded resources section of IV Ignite. So please definitely check that out. There are so many resources. We've got videos and courses and content available there that I find really helpful, that I use internally every day. So I highly recommend. I'm very excited about the J value calculator. I think it's really cool. We can go to our next slide. Like I mentioned, we have a lot of resources on our website. We've got our IV Ignite Online Learning Academy. It's sort of like our ICP conference, if you're familiar, but in a virtual form. It's on demand. It's a little bit more accessible than traveling for a conference, and you can do it at your pace. So it's a really great alternative if you're interested in our ICP conference and you're not sure if you're going to be able to attend. I would definitely check that out. We have our Bench Boost podcast. We go through a lot of the resources on our website, and we discuss them. We talk about questions and problems that we've seen in the different guides and the chapters individually. So it's a little bit easier to digest and you get some background information. And we also have included frequently asked questions through our technical support calls and emails and things like that. So when you guys reach out to us, we do really take into account, what problems you guys are seeing and what you would like us to talk about more in depth. So please don't be shy about reaching out to us. We love to talk about these things. We really love to help you guys out. And then all of our educational resources, our white papers, and things like that are available on our website at that last QR code. And then I think we have one last slide. We have our ICP workshop. This is a traveling version of our ICP conference. So we will go out into the world and kind of deliver the same type of information, which again, might be a little bit more accessible if you're living, we're on the East Coast in the USA. So if you're farther away and it's difficult for you to get to Virginia, definitely check out some of these alternative workshops. This one, registration has not opened yet, but we expect it to open sometime next week. So definitely keep an eye out if you're interested in that. And I think we are ready to go ahead and take questions. So looks like we've got a good one for Autumn, the arsenic 3 and 5. How to digest rice and to be sure that arsenic 3 is not being converted to arsenic 5.
That's kind of difficult because so for rice, generally we would recommend microwave digestion if you have a microwave um, with nitric acid to oxidize that organic. However, that will convert the arsenic in that sample to arsenic 5. So if you had arsenic as arsenic 3, um, you would have to keep that away from oxidizing agents. So generally, like with the arsenic trioxide, you would do a digestion in a basic matrix because it's really not even soluble in water. So my recommendation, so I'm not sure um, why you would need to keep it as arsenic 3 because you're still going to be quantifying all of that arsenic that was in there once you do the digestion. So even if you have arsenic 3, doing the acid digestion and getting all of the arsenic into solution um, as arsenic 5 is still going to, those results for arsenic are going to tell you the total amount of arsenic that was in your sample to begin with. So I am not entirely sure of a way to you would be able to get a complete digestion of the rice while also keeping your arsenic from being oxidized, because to get the rice into solution for an ICP analysis, you would have to do an oxidation to burn up those organics. So my recommendation, if you're just looking for the arsenic that's in that rice, even if it is arsenic 3 to begin with, my recommendation would be a digestion of the rice and then testing it versus the arsenic 5 standard. Don't think we have any other questions. But
It looks like we've got a question about our ICP True Rinse standard that we recently launched. So how does that compare to traditional hydrochloric or nitric rinses in terms of effectiveness?
Yeah, so for sticky elements, it depends on which one that you're looking at. So specifically for mercury, a nitric rinse is just going to increase your issues with carryover or with washout of mercury because that makes it more sticky, more likely to absorb to those intrasystem components. Hydrochloric acid works a whole lot better than nitric acid, so that is going to help to wash out the mercury. But adding the thiourea, which is what's in ICP True Rinse, what that does is it kind of surrounds the mercury and other heavy metals that might be present so that it doesn't have the availability to bind. So in combination with the HCl especially, it forms kind of a complex with the thiourea and the chloride and allows that complex to then move throughout your system and be removed more easily. So it works in conjunction with the chloride, but it is going to be more effective. And we do have a flip book available on our website that talks about ICP True Rinse, how it works and its effectiveness. I did a few washout studies comparing it to other rinse schemes. So if you're interested in that or if you're having washout issues, definitely check that out. Also, reach out to us if you're having washout issues and you think ICP True Rinse might be something appropriate for you. Because while it is a really good rinse for certain things like mercury and other heavy metals and precious metals, anything that's sticky, osmium is another one. I don't know if anyone, a lot of people don't analyze osmium, but it is in this method, so that's going to be something sticky, and it works really well for osmium and gold as well, but it may not work for what you're seeing carry over for. So reach out to us and we'll be able to recommend a good rinse scheme. We analyze everything, so we have to be pretty creative with coming up with rinse schemes to make sure that everything is getting washed out before the next samples.
All right, so it looks like we don't have any other questions in the queue at the moment. So if you guys think of anything, if you're looking back through the slides or something occurs to you later, please don't hesitate to reach out. You can go through our website contact request form on the website. It'll be at the top of the homepage. There's an orange button where you can email us at info@inorganicventures.com. And that will come straight to us in the tech support team, and we'll get you the answers to your questions, if we're able. Hopefully we're able. Usually we are. So yeah, if you guys have any additional questions, please let us know. But otherwise, thank you for joining us today. Thank you for your attention, and we look forward to seeing you at the next one.
Thank you, guys.